Let's do some examples. So I have CS and F. So I have CS, is that a metal? I see CS is over here on the left side, which means it's to the left of my staircase. It is a metal. It's also in group 1. It has one kind of charge. So this is a type 1 compound. And as you can see with all these that we're about to name, they are type 1 in this set. So I just name it cesium. And then I see I have fluorine, which becomes fluoride. And this compound is cesium fluoride. I can check the same thing. Aluminum with the next one, Al, is considered a metal. It's not part of the transition metals. I told you that's one you have to memorize. It has only one charge. So we have aluminum, and then chlorine becomes chloride. There's an L there, chloride. My last one, lithium. Lithium is right here. And lithium is a metal with one type of charge. And hydrogen is tricky because remember, hydrogen is right here, but it's still a non-metal. So since it's a non-metal, this one is lithium, and hydrogen becomes hydride. Okay. Go ahead and try set 2 on your own. Same process. You don't need to worry about Roman numerals for any of these type 1 compounds. Welcome back. Again, you'll have an opportunity to check your answers after this lesson. Let's go on to some type 2. These are ones we all need to use the Roman numerals for. So how do we figure out the Roman numerals when we're given a formula? Well, first you need to figure out the charge of the anion, so the second element. So in CuCl, I see that Cl is my anion. That is in this column here. As we said before, anything in that column has a -1 charge. So charges have to be balanced. If we're making sure the charges are balanced, if I have one Cl with a 1- charge, then the copper has to be a 1+. If the charges are the same, they balance out. If they're not the same, we're going to use a crisscross method to figure out our charge, and I'll show you that in a minute. So since these are the same, this ends up being copper 1 chloride. If I look at the next one, I've got Hg and O. Well, oxygen, based off of its position, is a 2- charge. So Hg, there's just one of them. This also has to be a 2+ charge. So this would be mercury 2 oxide. There's actually technically another way you could write it. There's an old nomenclature system where it refers to mercuric and mercurous. Mercuric refers to the +2 oxidation state. Mercurous refers to the +1 oxidation state. But mercury at 2 oxide is fine for what we're doing. With Fe2O3, this one's tricky because with Fe2O3, you know oxygen is a 2- charge, and iron can't be a 2- charge because the atomic numbers, or not atomic numbers, the subscripts are different. So what I'm going to use is I'm going to use this reverse crisscross method. We're going to use the crisscross method later to write formulas, but we're going to use this method right now to help us get started. So if I reverse crisscross, the 2 goes up with the oxygen, the 3 comes up with iron. This ends up being iron 3 oxide. Now, the way I know that works is because if I have 2 irons, each of them a +3, and I have 3 oxygens, each of them a -2, then in total I have a -6 charge contributed from my oxygens and a +6 charge contributed from my irons. +6 and -6 do balance out, and we end up being electrically neutral. Okay. So you might want to use that to help you work through some of your problems. Now, similar idea with manganese. So MnO2, I've got a -2 charge for oxygen, but I really have two -2 charges because I have 2 atoms of oxygen. The only charge the manganese could be is a +4. So I would end up with manganese 4 oxide. And I'm going to do one last one, and I'll let you practice some more on your own. And that is lead Cl is -1, but because there's two of them, again, there's two -1s because of my subscript here. There's one lead. Lead has to be a +2. This is a lead 2 chloride. So you do have to do some backwards thinking here. You have to figure out your charges and how they're balanced currently in order to work backwards to find your Roman numeral. So go ahead and try some of those for set 3. All right, welcome back. Exercise 5 is actually one that I think I'm going to skip due to time, but if you have a mix of type 1 and type 2, it really just comes down to looking at the first element and seeing if it needs a Roman numeral or not. So CO is here, it's a transition metal. Transition metals need a Roman numeral. So I'm just going to go through and label. I need an R for this one. When I look at calcium in the next one, calcium is over here. It is not a transition metal, so I do not need an R for that. Aluminum is one that we said had only one type of charge, so I don't need a Roman numeral for that. But then chromium, Cr, is right here. That is a transition metal. So I need a Roman numeral for that. If you go through and sort them ahead of time that way and just label the ones you know need Roman numerals, then the naming should come pretty easy. I've left plenty of practice in for you on that particular type. Now, naming polyatomic ions. I actually think this is one of the easier ones to do, but it can get tricky because the recognition piece is dependent on whether or not you have them memorized. So we're going to follow the rules just like we did before. I've got Na2SO4. I know that Na is sodium, and I know that it is a group 1 metal. So I don't need a Roman numeral. And SO4, this entire thing, SO4, is the sulfate ion. And so I name it just as is. I don't have to worry about "ide" endings. Here I see K, and then PO4 is a polyatomic, and that is potassium phosphate. Now, I haven't talked about my process for this so far, but I think it's worth noting that all of these elements are not binary compounds anymore because there are more than two elements here. If there's more than two elements, that's a big tip-off that you need to use a polyatomic ion in your name. So if you see more than 3 or more than 2, we're going in the land of polyatomic ions, and you need to dust off the cobwebs there for those ones that you've memorized. Here I see iron, manganese, and those are actually the only two that I see that are going to require Roman numerals. So I do need to know my charges here. So I've got one Fe, and then I have the NO3 group. The NO3 group has a 1- charge, but it's in parentheses, and there's 3 of them. So really that means I have 3 -1 charges. So in order for iron to be balanced out, this must be a +3. So this would be iron 3 nitrate. So you do need to look at those coefficients, or not coefficients, subscripts. Um, again, this subscript on the outside tells me that I have 3 sets of NO3. If I were actually to diagram this out, I would have one Fe3 plus ion. NO3 would be one big group with a 1-, and it says that I've got 3 of them, right? So in total, I've got 3 nitrogens, 9 oxygens, and 1 iron in this compound. That's a lot. So keep that in mind when you're looking at some formula writing things, okay? Some other common ones to be aware of. I'm not going to do every single one on here, but NH4, again, if you see N as the first element followed by H4, that is ammonium. That is still a polyatomic ion. So we name ammonium, We know it has a 1 plus charge, and then we got chlorine, so chlorine just becomes chloride. Um, Ammonium is the one you're going to have to look out for because it's the only positive one we're dealing with. So just be on the lookout for that. Not to be confused with NaHCO3, which is sodium, and then HCO3 looks like carbonate, but is actually bicarbonate, which, fun fact, that's your baking soda, sodium bicarbonate. This one is also interesting. OCl is a popular way to write this polyatomic ion, which is hypochlorite. So if you see OCl or ClO, it means the same thing. For whatever reason, conventions, they've written it as NaOCl. Sodium hypochlorite is actually in your bleach. It's one of the active ingredients in laundry detergent and bleach and things of that nature. All right, go through and try a set on your own. Okay, welcome back. Binary covalent compounds. This is the third type that I was talking to you about. These ones we're not going to see as much, but it is good to know how to decode them. The chemical formula will contain two nonmetals, both lying near each other on the periodic table. They may look like polyatomic ions, but they are not polyatomic ions. They're only polyatomic ions if there is a charge. So they're similar in the fact that you name the first element as normal and the second one with an IDE ending, but we have to use prefixes to tell us how many atoms are present in our molecule. If a vowel is present as the first letter of the second element name, we're going to drop the A, and I'll show you some examples of that in a minute. And then the mono prefix is only used for the second element. So a lot of these look similar to what you've used maybe in a geometry course, but the first four might be a little different. Mono, di, tri, tetra is 1 through 4, but then once we pick up with penta on, it's the same as you would with like a pentagon or a hexagon to determine the number of sides. So let's do some examples. This first one, I have 1 phosphorus, chlorine, becomes chloride, and I'm going to leave some space because I need to put in my prefix. And there are 5 chlorines, so I need the prefix penta. This is phosphorus pentachloride. In the next one, I've got 2 nitrogens, so I use the prefix dinitrogen. And then I've got penta and then oxide. Now, this is where that thing I talked about dropping the A if there's 2 vowels together. This looks like pentauxide. That sounds weird. It looks weird, and it's just not written correctly. So we're going to take out the A, and this is going to be pentoxide. Flows a little bit better, looks nicer, easier to pronounce. Okay. NO. So here we've got nitrogen, and we only have 1 oxygen. Again, we use the mono prefix only for the second element. Now I'm going to write this incorrectly again so you can stress the point of 2 vowels together. This looks like monoxide, which is just weird. It looks ugly. It doesn't sound right. So we're going to take out one of those oxygens, and we get monoxide, which sounds like something familiar. We've heard of carbon monoxide before. This is nitrogen monoxide. Okay, it's pretty much the same process every single time. Go ahead and try the next few and also work on the you try it set. All right, welcome back. We've already brushed on some formula writing real quick, but I want to give you some strategies if you're given names and have to go the other way around. So first, write the element symbols present in the compound. The cation is first, the nonmetal or anion is second. Determine your charges using the periodic table. If you have a transition metal present, that Roman numeral will come into play. That will tell you the charge of the cation. If there's a polyatomic ion present, that means you got at least 3 elements in your formula. Use the charge of the entire polyatomic ion. If charges are equal, the compound is electrically neutral, the formula is written correctly, and you're done. Just take the charges out. We only write a formula that has the elements and the subscripts, meaning the numbers below the element. That tells us how many atoms there are. If the charges are unequal, we're going to use the crisscross method that I mentioned before to balance charges. We've already had some practice with this because we've had to work backwards to find the Roman numerals. So this is just going to be more practice with some of the same stuff. If their subscripts can be reduced to a smaller ratio, simplify them. I'll show you that in an example in a minute. Use parentheses to keep polyatomic ions grouped together. Put the new subscript on the outside of the parentheses and leave the polyatomic subscripts alone. Never change the subscripts to a polyatomic ion because that will change its identity. There's so many times I've seen someone write NO3 on their paper and then they know they need 2 sets of NO3 to balance out their charge, so then they change it to NO2. That is wildly incorrect because now you have changed the identity from nitrate to nitrite, and that is not what we're doing. We need just 2 sets of nitrate. So I'll show you that in practice in a little bit. When we write acid formulas a little later on, treat H as a +1 charge, and that will help us to balance our charges. So some examples here, I had potassium and oxide. Potassium had a 1+ charge, oxygen had a 2- charge. Those charges were not equal, so we had to crisscross them. The 2 comes down after the potassium, so we have 2 potassium and 1 oxygen, and we see that those charges do balance out. So you get a K+, and an O2-. So since there's 2 O's, or 2 K's and 1 O, we end up with K2O. With iron 3 chlorate, ClO3 is the entire chlorate ion. Once you write the polyatomic ion, do not change anything about it. You'll see that the 3 has to come down on the outside here. If you just put the 3 on the outside, it looks like you've got 33 oxygens. That looks weird. That's why we need to use parentheses to tell us that we really have 3 sets of the chlorate ion. So it's important. It really, really is important to make sure that you're not changing anything inside once you've written it. When we're looking at sulfite, tin sulfite, it's 4+ and 2-. You'll notice here that we end up with a 2 and a 4 as our subscripts. Since each of these can be divided by 2, then 2 divided by 2 is 1, 4 divided by 2 is 2. We end up with 1 tin and 2 sulfite ions. So Sn, and then in parentheses, SO3, close parentheses, and a 2. Let's do a couple more together. Make sure we got the hang of this. Aluminum is a +3. So we got that 3+ charge. Cl is a 1- charge. Those are not equal, so the 3 has to come down here. And my final formula is AlCl3. If I've got cobalt bromide, I've got CO with a 2+ because that Roman numeral 2. Br is a 1- charge. They are not equal, so I need to crisscross them. Again, we don't usually write the 1s when we are writing our formulas, so CoBr2 is sufficient. Lead sulfate, this is a fun one because there's multiple things to pay attention to. We got our 4+ charge, and then sulfate is SO4 with a 2- charge. We're going to have to crisscross these charges. So in the process, we get Pb2 and then SO4, and we did put a 4 on the outside. It's not SO44, it's SO4, and there's 4 of them, so we need parentheses. But these can be reduced, so we get a final answer of PbSO4 2. Similar idea, we're going to try one with calcium nitrate, 2+ charge, NO3, and that has a 1- charge. The 2 needs to come down on the outside, and we get calcium, NO3. Again, we don't change the 3, but we did add a 2. It's not 32 oxygens, so make sure you throw in your parentheses. And that's really all there is to formula writing. I've come up with a grid with plenty of practice for you, and essentially you just need to write the formula in the grid. I see Ag plus, and I see N3 minus. If I switch my charges and turn them into subscripts, for example, this would be Ag3N. And you're just writing the formula in each box. All right. Our last little chunk here is acid nomenclature. It is based off of the presence of oxygen in our anion, and that's how we name our acids. If there's no oxygen in your anion, then it's considered a binary acid, meaning there's only two elements. So we use hydro to represent hydrogen. We use the anion root, and then the ending is ic acid. And so I'll talk about some of those. You've probably heard of hydrochloric acid. Hydrochloric is HCl, is chlorine. The chloro root becomes chloric. If there is oxygen in your polyatomic ion, we're dealing with, if there is oxygen in your acid, that means you're dealing with a polyatomic ion. You have three elements, and so the ending of your polyatomic ion will determine the root of the acid name. We use us acid for ite and ic acid for ate. So I will talk about that in a minute. There's no need to represent hydro in the name when dealing with acids that have polyatomic ions. All right, so this first one, hydrogen, we got hydro, sulfur becomes our root here, and we change it to ic acid. This is hydrosulfuric acid. If we're looking at this next one, we have the sulfate ion. So sulfate means we have to change it to ic acid. Now this one's going to be weird because even though it's sulfate, they end up calling this one sulfuric acid. So some of these we are just going to have to memorize how to name them. Phosphorus is a weird one because you've got the phosphate ion, whether it's phosphorus or phosphate, you end up with hydrophosphoric acid or you end up with phosphoric acid. So actually, I'm sorry, I made a mistake. This is phosphite. So actually, this is phosphorus acid because I ended with ITE. Remember, if it's ate, it's ic. Ite is us. And then if it's a binary acid, you got to put hydro in front. All right. Some other ones. C2O4 is not one we've seen before, but that's a good polyatomic ion. That is oxalate. C2O4 is the oxalate ion. If it ends in ate, it becomes oxalic acid. And then I like looking at the difference here with all of these bromine-containing ones. HBr is binary, so it's hydrobromic acid. But then when we get to BRO, this is very similar to the chlorate family. We haven't talked about bromate yet, but bromate performs just the same as the chlorate family. Here is our bromate ion, BRO3, and then you can guess that this must be bromite, this must be hypobromite, and this must be perbromate. So using those naming tools before, we're going to work through them. The first one is hypobromite. So this becomes hypobromous acid. So this is E, this is F. G is bromite, so it's just bromous acid. H is bromate, so it becomes bromic acid. And then I is perbromate, so it becomes perbromic acid. Oops, running out of space here. All right. So it's very systematic. You have to use the same format every time. Go ahead and try working through the you try it set. Now, again, just like we did with formula writing, this is a formula writing chore as well. If you're given an acid name like hypochlorous acid, remember that H is a +1. So ClO O is hypochlorous acid with a 1 minus charge. To be balanced, you have to have a +1 charge. So you could say HClO, or as I mentioned before, sometimes it's written HOCl. That would be our first one here. That's one, just an example of formula writing, so we haven't done that yet. All right. And that is the end of this lesson. I know it ran a little long, but it was important to cover through all of our nomenclature. Make sure you check your answers after completing the assignment. Have a great day.